let's continue and show a second approach for doing hypothesis testing. So this is the standard way using mathematical models. Reminder, what we're trying to do is measure. So the sample we analyzed, Amy is analyzing, she observed the two groups, employees with statistics training, employing without statistic training. And the observed difference is 130 EOV units. And our question is, how likely or unlikely is this value under the null hypothesis? The null hypothesis is that there is no difference between the two groups. Here is it in math, that there is some, the distribution for employees who took statistics and the distribution for employees who didn't take statistics, we assume they have the same mean. And remember, when we studied the estimators, we already built the model. We studied, we obtained a mathematical model for the sampling distribution of the difference between group means. This being the mean of the sample with of the group with statistics, and this being the mean of group 2. So the model said that the mean of the sampling distribution is the difference of the two means. If the distributions are the same, then the mean will be 0, and the variance is going to be the sum of the variances scaled by the size of the groups. So you can look back up in the notebook and find this formula. So that's great. We have a formula that tells us what the null distribution is. Only one little problem here is that the formula requires us to know the value of the population variances, which we don't know. We can, however, approximate these values with the sampling, the variance, the sample standard deviations, or the sample variances we obtain from the observed sample. So this is why it's going to be an analytical approximation. If we knew the population variances, then we would have an exact formula. There wouldn't be approximation. But because we're going to do this approximation of the unknown variance with the variance obtained estimated from the sample, then it becomes an approximation. In fact, there are two types of formulas to use. The pooled variance is a special trick when if we assume the variance in each group is the same, then we can combine the two samples and say what is the variance of the distribution. Because they come from the same distribution, we can pool the two estimates together to obtain a more precise value. And this is, as we see in the formula, without any pooling. So the values for the sample, for our analysis, they will come out to be about the same. But I wanted to mention, depending on how your teacher chooses to present the topic, they might ask you to do this, or some mixture of the two. Okay? So the key here is that we don't have the population variances. We're using only this approximation based on the sample. And that's where the student's t-distribution comes in. So every time you do, and the whole procedure is going to be called the student's t-test, because we're using the student t-distribution. It's a little complicated to explain, and we're going to do that in the book in more details, but the only thing you need to know is that these normal distributions are the correct model. But when we're going to do some estimation, we're not going to be plugging the real values, right? We're doing this, replacing the population variance with these estimates. So this means we'll underestimate the variance. So in order to protect, sort of defend against that, we know that whenever when we use this, we'll be underestimating. the t-distribution looks like the normal, but it's a little bit wider. So there are longer tails, the mass, it's not the same shape, it's actually a little bit longer tail distribution. And the specific shape of the t-distribution counterbalances the fact that we're using estimates. That's how much I want to say. And the dependence, the t-distribution is not like one distribution. They're actually a family, and they have a parameter called the degree of freedom of the t-distribution. So a lot of the formulas you're about to see will have this degrees of freedom, which we need to calculate. And roughly speaking, the degrees of freedom are proportional to the sample sizes, minus 1, minus 2 usually. And sometimes it's a more complicated formula, but I choose intentionally not to focus and explain these in detail, because that would take us too far out of field. But trust me, like if you understand this, and the t-distribution and the degrees of freedom are just necessary, because we are not actually having the real normal. We don't have these values we're going to be approximating. So by choosing the t-distribution, it balances out. So if you understand how it works with the normal, the t-distribution is just a more accurate way to do that. Okay, so how do you run a t-test? Is there anything? You just import the t-test for two independent groups, comparison of two independent groups, from cp-stats, SciPy. You get the data for each group and run the test and print p-val. Wow. So this is what I call the black box approach. We didn't touch any t-distribution. We didn't inside this function. All the work is done. So in practice, when you're using statistical software, this is what you're going to do. You just run the function, and all the complicated calculations are hidden inside here. No, this is not our way though. The no bullshit way, you gotta know the details. So what goes on in here is this 6-step procedure. So at the risk of being showing this is too complicated, I want you to just quickly be exposed to what's going on inside this function. Okay, so what's going on is we'll need the t-distribution. We'll compute the two means and the difference between the mean in the two groups. So as previously. Then we're going to compute the standard deviation from the samples. Okay. The sample sizes are important too. Then here is a complicated expression for the pooled variance. The pooled standard deviation is the square root of the pooled variance. So remember, this was this model here where we say under the null, the variance comes, they're the same distribution, right? The null, they have the same, okay, we assume these are, the variances are the same. So in that case, if we have the two estimates, we can pool them together to get a better estimate. Okay. Then the actual standard deviation of the sampling distribution of capital D is called, there's a name for it called the standard error.
It's 9 o'clock.
And then the t distribution is just the difference divided by the standard error. The degrees of freedom are the total samples, the number of combined sample size minus 2. And the p-value is when you obtain the t-statistic, you're interested in where exactly does that fall within the t-distribution. When you get that answer, it will be a one-sided p. The p-value will be half its true value, because we need to multiply times 2 to get both tails. And when you run all these steps, you get exactly the same number. Wow. So literally what you see here is what's happening under the hood here. Okay, so why did we need to do this? And why? Because for the past 100 years, when people have been doing statistical analysis comparing two groups, have been following this procedure. I know it's complicated, I know there are a lot of formulas, but trust me, this is as complicated as it's gonna get. So don't be freaked out by this. Mitigating factors. One, you don't need to do this step. I'm showing you this just so you know what's happening behind the scenes, but you don't need to know this. In practice, you need to know when to apply the t-test and just run the procedure. It will do all the steps for you. So your job will be to know when is it appropriate to use the student's t-test. Okay? And even better, you don't need this approach too. This is just one of the options. You can always use the permutation test. So you have a lot of options here. So don't be freaked out like, oh my God, I will never, this is too complicated. I'm gonna skip this part, but it's an equally important, it's another procedure similar to this that gives you a p-value, but these steps are different. Instead of using the pooled, actually these steps, the actual computation is the same. Instead of using the pooled standard deviation, we use the unpooled. So it will be a little bit less accurate, but applies in more cases, applies in more scenarios. Okay, let's summarize. We have an answer to question 1. The answer to question 1 was, how likely or unlikely is the difference D130 to occur by chance under the, if there is no difference, or in a hypothetical scenario. All of this we did here has nothing to do with the real world data, right? The model we used is under a hypothetical scenario where there is no difference between the two groups. Remember the skeptical colleagues that says, Amy, no, I don't believe you. There is no difference between statistics employees who did statistics and employees who didn't do statistics. Amy can now go to this employee and say, look, the observed value 130, if there was no difference, it will be only 0.04.6% chance of seeing it under the null hypothesis. So by all conventional methods and standards, it's unlikely for this to occur. Therefore, there is a difference. And that's what, so the question 1 was, is there a difference between the two groups? Yes, there is. And all these tests show it. Okay. Next video, we'll actually address the useful question. How big is the difference between them? Now that we know that there is a difference, we can ask the real question, how big is the difference? In other words, effect size. See you in a few minutes.